Okay, so now the recording is going on. Then the speakers have the floor. Thank you. You can go ahead now.
Thank you very much, Fernando, for your nice introduction. I'm David Perez, manager of Solar Division in Altran Technologies. Good morning, good afternoon, good evening, good night, everybody. Welcome to this CSP Industry Technologies and Markets event webinar co-promoted by CSP Today, following a report developed recently about drivers and barriers in the current CSP market. The contents of this webinar will be first a short introduction about who we are, Altran Group. After that, we will go in depth about basis of CSP technology, focus in Parabolic Trough, central receiver, linear Fresnel and these systems. After that, we will see CSP performance per technology, cost, market issues, drivers, barriers, value chain, and last one, worldwide capacity in megawatt. And after that, we will discuss some conclusions. Altran Group is an innovation partner, global partner company with presence in more than 40 countries, with own office mainly in Europe, Asia, Americas, and other countries where we are developing our activity. Altran is a best-in-class and world leader in consulting and innovation. Has currently 18 employees working in consulting and engineering domain. 90% of our employees are engineers, and we are focused in three main areas of interest: strategy and management, with our company Arthur D. Little, organization, consulting, and IT, and last one, technology, engineering, R&D, and innovation, with presence in all market sectors. Altran Group, as I said, has several markets with priority. These markets are automotive, aerospace and defense, energy, life science, industry, telecoms, media, electronics, and finance and government. Energy division is where we are located, and we are divided in conventional energy and transport and distribution, and on the other one branch in renewable energy. In renewable energies, we are working around the world in efficiency, in biofuels, in hydrogen, wind power, and the team I'm in charge of is focused on solar activity and solar technology. Altran activity in solar domain includes mainly to provide consulting services and engineering to technological company, promoters, and EPC, engineering, procurement, and construction company, covering all the technologies in solar, PV, CPV, and CSP. In last one, covering cylinder, parabolic trough, tower, and Sterling mainly. Our main competencies, where Altran is an excellent partner, are R&D, where we are world leader in innovation methodologies and innovation systematic, product development, product optimization, where we have done dozens of projects related with that area, process optimization, and last one, project support and development to promoters and EPCs company, where our main role is engineering, technical office, owners engineering, including execution control, technical audits, commissioning, and where we have a huge experience in energy sector. Last one, experience in after sales, warranties, and operation and maintenance. Okay, next point is going to be developed by presented by Juan Manuel Martin.
Hello, good evening, everybody, or good night, or good morning. It's an issue to talk to people that are in very different areas in the world. I am going to try to set a few points related to the technology of CSP industry. And first of all, I would like to introduce a few questions that we are going to an answer for these questions in the next slides. First of all, we are going to try to respond the question, which are the most important technologies related with the thermal application of CSP, or which are their main advantage and disadvantage, or which technology is the most developed and mature. Also, we are going to try to answer the question about what are the real investment costs, and finally, which are the expectations for the near future related to these technologies. You can find a more in-depth study about these technologies in the report that CSP Today has published a few days ago, a few weeks ago, sorry. And we are going to outline only a sketch for answering these questions. First of all, we are going to review the basics of the CSP technologies. As you know, there are four main technologies related to the CSP, mainly the solar trough technology. Also, we have the tower and heliostat technologies. We have the Fresnel lens technology, or linear Fresnel technology, and finally we have the SLR Dis technology. Typically, a CSP plant is made basically by a solar field and a power isle. The solar field is the component that makes the difference between each type of CSP technology. A typical solar field is composed mainly by a concentrator, in which the solar radiation is multiplied several times in order to increase the power density. Then we have a solar receiver that converts the solar radiation in thermal energy. And finally, we have a set of optional elements, like for example, the thermal energy storage, or a hybridized steam generator. Okay. The power isle is mainly composed by a heat recovery steam generator. The main function is to generate the steam that is going to run the turbine of the CSP plant. Then we have the steam turbine to convert the thermal energy in mechanical energy in an output shaft, and then we have an electric generator to convert this mechanical energy in electrical energy. Other points dealt that we are going to comment and that you can find in the CSP report are a brief history of the CSP technology and the current status of these technologies, a description of the different technologies and configurations related to the CSP technology, and very in-depth description of energy storage systems and the different technologies used to resolve this important issue related to the CSP plants. And finally, you are going to find also the more important requirements related to this class of power plants. For example, solar DNI requirements, the direct normal irradiation that is required to run a power plant, a CSP power plant. You also are going to find the load requirements, the land requirements for this class of power plants. And finally, you are going to find the water usage of this kind of plants. That is also a very huge issue to run this kind of power plants. Okay, if we go more in depth in each kind or type of CSP technologies, we are going firstly to review the Parabolic Trough system. This slide shows a collection of the more important parameters on this kind of technology and a typical configuration or layout of this plant. In this plant, the solar field is made by a big assembly of parabolic-shaped collectors joined in different loops in order to achieve the required temperature to run the steam cycle of the steam turbine. Well, as you know, by the solar field runs a high TF fluid, a heat thermal fluid, in order to get the energy from the sun, and then this heat or this thermal energy is converted in steam in the steam generator of the power plant. Okay, as Fernando is doing, he's pointing out the solar field of this layout that we are seeing in this slide.
You can also point. You can use your mouse and then point on the parts of the presentation. Okay.
Okay. Well, let's see. Okay. Then you see the solar field of the power plant. Here you can see the heat recovery steam generator, in which the heat concentrated by the collectors is converted in steam to run the steam turbine. Then you can see different optional elements for the solar plant. For example, the energy storage of the solar plant. Also, you can see an hybridized boiler, mainly run by natural gas or biomass or something like that. And finally, you can see the power eyes, the turbine of the power plant with the condensers, the aerators, and so on to complete the steam cycle. Okay. Okay, next table shows mainly parameters related to the performances of this kind of solar plants. For example, you can see the typical power plant in a range between 30 and 300 megawatts. Also, you can see the annual capacity factor of the power plant. This factor is defined as the ratio between the annual generated energy and the generated energy if the plant always runs in the nominal power for all the year. Also, you can see the peak efficiency of the power plant or the annual net efficiency. Then you can find the maximum temperature of the cycle between 300 and 400 degrees. The kind of cycle that is run in this power plant is a Rankine cycle. The typical concentration factor that is between 28 or 85 mainly for different class of solar collectors, and then you can find typical areas for this kind of collectors that is related mainly with the length of the collector and the length of the loop of collectors. Finally, you can find the receiver absorptivity. It also depends in the class of collector used. And the typical thermal storage that can be used, we can find plants with no thermal storage to plant with 12 hours of thermal storage with an aim to extend the operation of the power plant when there is no sun availability to run the steam cycle. Then we are going to review briefly a central receiver or solar tower plant. This kind of plant, the main difference respect the previous commented trough plant is on the solar field. The solar field is composed by a huge number of heliostats that points the solar radiation in a point located in the upper part of the tower, and here you can find the receiver of the tower. Okay, then solar radiation is reflected by a heliostat and concentrated in the receiver located in the upper part of the tower. This heat concentrated in this receiver is then evacuated by a thermal fluid that can be air or molten salts or even water, in order to collect this solar energy and then convert into steam in a steam generator of the power plant. The steam generated then is driven to the steam turbine in order to produce the electricity. Here you can find also some of the more important parameters related to this kind of power plants. For example, the typical power plant for this kind of plants is in the range between 10 and 200 megawatts. Also, you can find the annual capacity factor in the same basis that was defined before. You can find also the peak efficiency of the power plant, or the annual net efficiency of the power plant, and also the maximum temperature of the cycle. As you can see, this temperature is quite higher than the maximum temperature in a solar trough power plant, and this give us a higher performance of the power plant. The cycle used in this kind of power plants is also the Rankine cycle, and you can find also some areas or surfaces for a typical heliostat used in a power plant of this kind. And finally, you can find the thermal storage, that is between 7 and 15 hours. This number, okay, it's no difference. There is no difference with the number before exposed for the solar trough power plant. It's only based on the current operating solar power plants that we have in Spain. Okay, let's go to review then the linear Fresnel reflector system. This kind of power plants are very similar to the solar trough power plants. The main difference is related to the solar collector. The main aim for this power plant is to reduce costs respect the solar trough power plants. So this kind of power plants use the cheapest elements, like for example mirrors, are flat shape mirrors, cheaper than the curved parabolic mirrors that are used in solar trough power plants. And also another important difference is on the solar receiver, and the receiver tube of the collector. The receiver tube is located above the mirrors, and then here you can find that is a fixed solar tube. So the joints between different solar tubes of different loops of collectors is simpler and then cheaper. Also, you can find here another table summarizing the main parameters that define the performances of this kind of plants. For example, you can find how the annual net efficiency of this kind of power plants is lower than the annual net efficiency of a solar trough power plant. This is due mainly because the maximum temperature of operation in this kind of plant is lower also. In the table, you can find that the temperature of operation is 390 degrees, but it's a mistake. Okay, this kind of linear Fresnel plants reach about 290 degrees, or as much 300 degrees. Okay. Then you can find another important parameters, like for example the water consumption of the power plant. mainly running the steam cycle of the power plant in order to compense the leakage in the steam cycle, or the water usage for cleaning the mirrors. Also, you can find the land requirements of this kind of power plants. These requirements are higher than a solar trough power plants, and also you can find the typical storage for this kind of plants. The range or the typical power of a Fresnel power plant is in the range between 2 and 200 megawatts. Typically, these plants are lower than a solar trough power plant because the land requirements are higher. And then we are going to deal with the last technology of CSP generation technologies, is the SLR Dis or solar Stirling or Stirling Dis system. This system is quite different than the previous we have reviewed before, because it's a very modular system, and the typical power in this kind of system is lower than that you can find in another kind of CSP plants. For example, we have that the typical layout of a solar disk is mainly a framework, a metallic framework that supports and gives shape to the primary concentrator of the solar disk. Then the sun radiation is concentrated by this primary concentrator in a secondary concentrator that also acts like a receiver. Okay, then you can concentrate the solar radiation about 1,000 or 1,500 times the nominal solar radiation in the location of the solar disk. The receiver acts like the hot source of energy for running the Stirling cycle, and then the Stirling cycle has the cold source for the cycle on a point where the redundant heat is rejected to the atmosphere. Here you can find some of the main parameters that describe the performances of this kind of system. For example, a Stirling disk has a very low power in the range between 5 and 25 kilowatts. So as you can see, to reach a typical power for a solar trough power plant, we can talk about 50 megawatts to 200 megawatts. We have to put together a huge number of solar disk units. Also, you can find the capacity factor of a typical Stirling disk systems. Also, it's important to point the maximum the maximum temperature of the Stirling cycle, that is about 800 degrees. As you can see, it's higher. It's very higher than the typical values that we have seen for a solar trough power plant or a central receiver power plant. So the peak efficiency of this kind of system is very high if we compare that with the peak efficiency found in a solar trough receiver or in a tower, on a central receiver or tower power plant. One of the main issues related to the Stirling disk systems is that nowadays there is no way to solve the thermal storage for this kind of system. So the system currently only can run the Stirling cycle when there is solar radiation available. This is an important issue that many companies around the world are trying to solve in a short term. Well, here we have a slide summarizing the CSP performance per technology. Well, the information it's well, it's put together in the CSP report, where you can find a more in-depth analysis about this CSP performance. For example, in the report you can find a performance comparison between different CSP technologies in a more in-depth way, so you can put together and compare these technologies. Well, I think in a very interesting way. Also, you can find in the CSP report possible performance improvement related mainly with the impact of a higher temperature of the cycles, trying to describe how an increase in the temperature, in the maximum temperature of the cycle, results in a very important increase in the efficiency of the power plant. And also you can find in the CSP report an analysis on the impact of a simplification of the system brought by the use of a direct steam generator, mainly simplifying the layout of the power plant, reducing the investment of the power plant, but making more complex the operation and maintenance of this power plant. And finally, I would like to show you a summarize of the current cost of CSP technologies in this moment. This cost has been calculated taking into account some general considerations, like, for example, the scale of the project and the scale of the power plant, the performance of the different equipments used in the power plant, the availability of solar resources, the different terms of financing the project, or the impact of taxes and regulations in the project. This study has been done for different technologies, and then you can find these technologies put together in order to compare the different parameters, different economical parameters for these technologies. In this slide, we have summarized the main economical parameters for the different technologies. In the report, you will find a more in-depth analysis, and also you will find more info about that. But here we think we can find very important parameters, like, for example, parameters related to the investment, mainly the initial investment without and with storage for different technologies. Also, you can, sorry, here you have this parameter, the initial investment cost. Also, you can find the initial investment cost only for the solar field as a percentage of the total investment for the power plant. Also, you can find the investment cost for the power block, also as a percentage of the total cost of the power plant. The initial investment related to the steam generator, or the initial investment for the control system of the power plant. Also, you can find the investment related to the O&M services along the life of the power plant, the cost of the balance of the plant, the cost of the energy storage of the power plant, and finally a very important parameter, that is the LEC, the levelized energy cost, that is the cost of generating each kilowatt hour for the power plant, and for each of the considered technologies. I think this is an important review of the main economical parameters that are associated for each power plant and for each technologies. Now, Rosa Blázquez is going to explain you the CSP market.
Hello, my name is Rosa Blázquez, and I am going to, after revising the main technical aspect of the CSP technology, I am going to talk about the CSP market, focusing our attention on the barriers and drivers of the current concentrated solar power market. The present global situation about environmental and economical issues opens a wide opportunity for CSP technologies development. Due to the necessity of reducing fossil fuels dependence and minimize greenhouse gases, as the 700 megawatts in operation and 2 gigawatts under construction show, CPS technology is entering a new growth phase. CSP has a high potential for late-scale power generation and technological improvements and are making it increasingly cost-competitive. In this emerging phase, pioneering countries such as Spain and United States occupy a privileged position and offer significant opportunities for the development of the CSP market. Demonstration projects implemented in countries like Spain have shown the commercial viability of plants with concentration technologies. Juanma, desactiva tu. Sorry. As I was saying, the main issues in the CSP market are the financial ones. Therefore, any government measure should focus on reducing the cost of the technology and providing the appropriate financial instruments to promoters. So now we are going to talk about the drivers. The CSP market is in a crucial moment to turn into the main renewable energy market in the short term. Some factors for this to become a reality. These are the drivers. First of all, the energy security. One of the leading threats to energy security is the significant increase of energy prices. Energy plays an important role in the national security of any given country as a fuel to power the economic engine. CSP can enhance energy security in electricity generation. This technology is the most efficient among the solar and good security for future energy supplies. Then the second driver will be the fluctuating price of fossil fuels. Oh, sorry. The fluctuating price of fossil fuels. The price fluctuation has an important impact in the economy of countries, sometimes even affecting the energy security. While the conventional energy cost continues increasing its cost, it is hoped that the CSP energy cost will be reduced. The job creation. Around 500 jobs are created during the construction period of a 50 megawatts CSP plant, and about 50 will be permanent for operation and maintenance during the rest of its life. Then the climate change. 70,000 tons of CO2 emissions are avoided with a 50 megawatts of a CSP plant. These are very important figures concerning all the issues related to environmental in the last times. Then finally we have the government incentives and regulations. The global and particular mandates of each country and the situation of the market also has an impact on the CSP market. Currently, it is important that governments provide with mandates and energy policies, including change in the research and development funds. Direction of the government in the sector of research and development in order to promote the CSP technology or to direct money to new projects. New technologies and centers of R&D. This is especially important for those less mature technologies, such as Stirling and the tower power. in order to reduce investment risk and to make possible the initial stage of development for these technologies. It is very important that governments provide with mandates and energy policies or incentives. For example, the feed-in tariffs like the one existing in Spain, or tax credits, tax incentives, etc. So we go to the next slide to talk about the barriers. Although CSP technologies have a great potential, they face a number of market barriers. To produce an efficient technology, it is desirable to minimize them. The associated risks vary between countries but may include political instability, insufficient legal and administrative structures, economic vulnerability, lack of infrastructures, and many more. The high capital cost of CSP technologies leads to a high levelized energy cost, and it makes project financing more difficult compared to technologies that are fuel cost intensive. Then the geographical risks. A very high DNI is required. A near water source is also required. A flat land and a good connection to the grid is needed for a CSP plant. Another barrier are the long permitting processes, which directly affect the total cost of the project. There is also a technological uncertainty with constant improvements and cost reductions. And finally, the lack of transmission capacity in the grid will limit the amount of power that can be exported. However, it is to be expected that the main future markets for solar thermal power will emerge in developing countries because of their outstanding solar resource. Let's go to the next one to talk about the CSP value chain. CSP is a new industry, and the roles and actors in the value chain vary significantly by technology and project. The value chain is still evolving. A value chain could be established with the next basic levels. First, materials, then components, then finished products including solar technology and plant development, then the distribution via ownership and operation of the CSP plant and use of the power by utility companies. In all the stages of the value chain, the research and development centers have an important presence. In the figure, you can see the whole value chain and the actors from the left side of the graph, showing the product development going to the system integrators, project constructions, EPCs, operation and maintenance companies, and final projects. As I was saying, the research and development centers are present along the whole value chain. We have the PSA and the CMAT, which are located in Spain, and then we have other centers with the NREL or the DOE in the United States. Okay. In the next slides, we can see some graphs showing the concentrated solar power capacity and projects worldwide. In the report of CSP, there is a section summarizing the projects around the world. First, we have the plants in operation, then the plants under construction, and then the planning plants. As an example, we have included here two graphs showing the worldwide operating plants and another one showing the worldwide plants under construction. In the first one, you can see the percentage of operating plants per technology. The parabolic trough, I don't see if if you can see it, the parabolic trough accounts for about 90% of the operating plants around the world. Then is followed by a Fresnel collector, this one, and a tower system with 7 and 5% each. Then in the second graph, you can see the existing plant under construction per countries. Most of them are located in Spain, this one, the blue one, with about 1,400 megawatts under construction. Then it's followed by this one here, which is Greece and Egypt. Other countries are Morocco, Algeria, USA, Australia, Italy, and France. Well, finally, as a conclusion of the report on the study developed by Altran together with CSP, we have some conclusions. The first one is that a high level of direct normal irradiation is needed for the operation of CSP plants. 2,500 kilowatts hours per square meter and per year is recommended. This requirement limits the geographical areas where CSP is feasible to the following areas. First, the Southern Europe, the Middle East and North Africa, Southern Africa, some regions in India, northwestern and central Australia, northern Mexico, southwestern and middle west of USA, and then the Andean Plateau. Another conclusion is that technological improvements are needed to reach a higher performance. Some of these are increasing the operating temperature, improving the energy storage systems, and reducing the water consumption to be able to locate these plants in other places. As we said already, Parabolic Trough is the most mature technology, followed by Power Tower and Fresnel, and the less mature is the Dis technology. The installed capacity CSP power capacity worldwide is about 700 megawatts. USA is the country with more plants in operation, with about 443 megawatts. Spain is the second with about 230 megawatts in operation, and it has also 1,367 under construction. When they are finished, Spain will be at the forefront in installed capacity with more than 1,500 megawatts. Reviewing the part of the drivers, we can say that the main drivers for the CSP technology development are the government mandates for renewables, the energy security, which is linked to the fluctuating price of fossil fuels, the job creation opportunity, the climate change, and the government incentives and regulation. Finally, the CSP technologies have a great potential, but nowadays they face a number of market barriers, such as political instability, insufficient legal and administrative structure, economic vulnerability, or lack of infrastructures. However, in developing countries, it is expected to minimize them in the near future. If you would like to have more information about the CSP, you can find it in the Global Concentrated Solar Power Industry Report 2010-2011. Here you've got the link to it. Yeah, and if you would like to have further information about Altran, here you've got the link to David Peret, who you can get in contact with. Thanks for your attention.
Okay, thank you very much, Rosa, for this presentation, as well Juan Manuel and David. very interesting presentation and very comprehensive. As it is pointed out here, the more comprehensive report is available at this link. You can point at it and then you will be directed there. The presentation and the recording of this webinar will be available in the Leonardo Energy website. I will put it the link in a few moments. Okay, so now we can proceed to some questions and answers. So I will give the floor to our speakers. I see that David lost connection, so I will try to keep him back. And then, well, I let you read the questions, select the ones which are more suitable. Then we will use this Q&A pod. Let me size in order to proceed with the questions. So please, Juan Manuel and Rosa, the floor is yours. You can select the questions, send them to the audience, and then answering. Thank you.
Thank you, Fernando. We are handing the questions.
Okay, great. So you can go ahead. Yes, for our audience, if you have a question, please type it in the Q&A window that is here enlarged. Then we will be managing your questions. Thank you. So now just be patient. Our speakers are reading them, selecting and preparing answers. Thank you very much. Meanwhile, I will take advantage to show the link to the Leonardo Energy webpage, where you can find the presentation and the recording in a few hours from now. Thank you.
Hello again. We are going to answer a very interesting question about what are the main challenges in thermal storage. Okay, one of the main challenges in thermal storage is rise up the the availability and reliability of molten salt energy storage. This kind of technologies have a very important issue about the reliability, mainly in the steam in the steam generator in the heat exchanger, in which there are put in contact molten salts and the thermal oil that flows in the solar field. There are very important issues about this heat exchanger, and this is one of the main challenges that are going to be researched in order to solve this problem. it's very important also another challenge about how to store the heat generated when you run a power plant based in direct steam generation. It's very important because you need to develop an energy storage based both in sensible heat and also in latent heat. So there are several research in the DLR in Germany in order to develop in a more appropriate way this solution for the energy storage in direct steam generation power plants.
Okay, thank you very much. So you can keep again some moments to select the next question. In the meanwhile, I can point out to the audience that the recording of the webinar and slides will be available in some hours at Leonardo Energy website, which is indicated in the note which appears in the main screen. So thank you very much, and now again the speakers, you have the floor. Thank you.
Okay, another interesting question that has been made. It's about what is what is the comparison between CSP technologies and PV technologies? Okay, I think these technologies are not comparable, mainly because the physical principles that run this kind of power plants are very different. For example, CSP power plants, it's possible to deploy a big power in a relative in a short land with short land requirements. However, in a PV power plant, to deploy the same quantity of megawatts, the land requirements are higher. So I think these kind of technologies are not comparable. We think that the future is it's very interesting for both kind of technologies, and it will be the promoters of renewables energies which will decide which kind of technology is more appropriate for different locations, projects, countries, depending, for example, on the regulation and so on. Okay, another important question is about what is the DNI and what are the requirements about this parameter. Okay, DNI is a direct normal irradiation. That is, as you know, the solar irradiation is divided in both direct irradiation and albedo, or diffuse solar irradiation. In this kind of system where concentration is very important, only the direct irradiation is possible to be used. The requirements for this kind of concentration system is about a very good pointing to the sun in order to take advantage of the maximum direct normal irradiation that is available in the location. In a typical number of required direct normal irradiation is about 200.5 kilowatts hour per square meter and per year. This is a recommended value, and values higher than this are very appropriate, but this value can be considered as a good value. Below this value, it's not recommended to use concentration technologies.
Very well, thank you, Juan Manuel. If you have still 5 minutes, maybe we could proceed with some additional questions. I see that there are many questions, so we will not have time to cover all of them. So we're trying to select the most representative ones. I see that people are also asking about support mechanism and grid integration policies. So I point out in the note pod a comprehensive report on advantages, disadvantages, and experience on different support mechanisms such as call to bids, feed-in tariffs, green certificates, and so on. So you can find this comprehensive report there. Do not hesitate to have a look. So in the meanwhile, I see that our speakers have selected another question on water use. So please, you can go ahead with this question. Thank you.
Okay, let's see. The water used per megawatt for cooling the power plant is very dependable on the technology used. For example, if you have a parabolic trough and you have also a cooling process based on a closed circuit, for example, you are going to have a minimum water demand of in a range of 760 to 920 gallons per megawatt hour generated. Okay. If you have, for example, a Fresnel technology using this cooling process based on a closed circuit, you are going to have mainly the same number. If you have a central receiver, you are going to have between 500 and 750 gallons per megawatt hour generated by the power plant. For example, in a SLR Dis, you don't have the requirement of using water as a cooling element, or even as a way to generate steam, because as we said before, the SLR Dis employs an Stirling cycle using mainly helium or air or hydrogen to run the power cycle. Okay.
Great, thanks. Thanks, Juan Manuel. This is indeed definitely an issue with solar energy. Good places for sun are bad places for water in general. So um, there is an everlasting question on water use. So indeed, if you have a power cycle like Rankine or whatever, then you need cooling. So either you can do dry cooling, but in this case you lose efficiency and increase investment, or wet cooling and other technologies like stirling, as Juan Manuel pointed out. The operating temperature is so high that it's no matter in cooling with air. So yeah, there is good discussion on this on CSP CSP Today website and other forums related to CSP Today. Okay, so I let you continue with these interesting questions. Thank you.
Okay, let's going to review a last question. For example, here we have a question about regarding the water issue. If the best location for a CSP plant is near the coast. Okay, it's very difficult to use water from the sea to run the CSP cycle because, well, as you know, water have a very huge previous treatment in order to obtain the suitable water to run the cooling cycle. For example, you are going to need an osmosis cycle in order to eliminate the salt and then introduce the water in the power cycle. But it's very interesting the point contained in this question because there are several studies in order to use CSP power plants in order to do the desalinization of water, and these studies give very promising results about the use of solar energy in order to produce potable water. Okay, so I think this is a very important point to follow in the short term, and in some countries, for example, in the north of Africa or in India, these applications can be very very interesting.
Okay, thank you very much, Juan Manuel. Thank you very much, David and Rosa. We have to adjourn now. So thank you very much to the audience. We see that this is a topic which generates a lot of interest. So see you soon in our webinar program. Do not hesitate to go back to CSP Today website, and especially if you are interested in global report. As well, you can be in touch with Altran Technologies specialists. And now we close the session. So I let the floor to the speakers just to say goodbye and any other message you consider. Thank you very much.